Hi, this recording is going to go through Activity 4. Some people did a really great job on this activity, but there were a number of people who seemed kind of confused by it, so I want to work through it and talk through what I'm doing. So the first thing we're going to do is we are going to look at the data from the sample of people living in Atlanta, looking at their mean commute time. We're going to be using the data to estimate the mean commute time among all people living in Atlanta. And we're going to go to STAT111 to get the data. Here I am in STAT111 and I'm making a bootstrap confidence interval for a single mean and selecting the data for the Atlanta commute time. Now I can see the data from the original sample over here, over here in the corner. And I can see the mean for the original sample is 29.11. That is going to be our sample statistic. The sample statistic always comes from the original sample. Now I'm also going to need the standard error, and the way that I'm going to get that is by simulating the bootstrap distribution. So I'm going to generate 5,000 samples. And now the standard deviation of this bootstrap distribution, which I find here, is 0.920. That's our standard error. Okay, so our standard error is 0.92. Now we want to find the 95% confidence interval that we used using the method from Chapter 3. So we take our sample statistic, 29.11, and we add and subtract 2 times our standard error of 0.92. This gives a 95% confidence interval going from 27.27 minutes up to 30.95 minutes. And 95% confidence the true mean time for commuting among all Atlanta commuters is between 27.27 minutes and 30.95 minutes. Now next we're going to make a confidence interval using the normal distribution method. And to do this I'm going to use the formula sample statistic plus or minus z star times the standard error. Now I have the standard error, but I'm going to get the z star from the standard normal distribution, so I'm going to need to go to STAT111 for that. Now to find z star, I go into the normal distribution. I make sure that the mean is 0 and the standard deviation is 1, which they are. That gives me the standard normal. And now I want to find the z star so that between negative z star and positive z star I have 95%. To do that I use the two-tail option, and I make sure I have 95 here in the middle, 95%, which I do. And then the z star value is going to be the cutoff down here on the bottom axis, 1.96. So for a 95% confidence interval, my z star is 1.96. When I want to make my confidence interval, I'm going to have my sample statistic, 29.11. plus or minus 1.96 is my z star, times the standard error, 0.92. This gives me a 95% confidence interval that goes from 27.31 minutes up to 30.91 minutes. Now comparing my two 95% confidence intervals, you can see that they are very, very similar. Now we're going to suppose that instead of a 95% confidence interval, we want to make a 90% confidence interval. And we're going to need a different value of z star for our formula because z star is determined by our confidence level. So let's find our z star for 90%. Again, we have to be in STAT111 in our standard normal distribution. The only difference is that now instead of putting 95% in the center here, I want to put in 90%. So I'm going to change my percentage in the middle to 0.90. And now the z star that I use for a 90% level of confidence is 1.645 down here on the cutoff. Coming back to my formula, but now using the z star for a 90% confidence interval, gives me a confidence interval that goes from 27.60 minutes up to 30.62 minutes. I can see that my 90% confidence interval is narrower than my 95% confidence interval. Now intuitively, why does this make sense? Well, remember that our confidence interval gives us a certain percent confidence that our interval contains the true value of the parameter. the more intervals the more values that are included in our interval, the wider the interval has to be, the better the chance that we are going to actually contain our true value of the parameter that we're trying to estimate. So to have more confidence, we need a wider interval. To have less confidence, we don't have to include quite so all those values, so we'll have a narrower confidence interval. Now in the second part of the activity, we're going to do a randomization test and a test based on a normal distribution for the proportion of NFL overtime games that are won by the coin flip winner. So we're going to test at the 5% level of significance to determine if there's strong evidence that the team who wins the coin toss is more likely to win in overtime. So the first thing we need is our null and alternative hypotheses. We're going to need to write them in terms of the parameter. If we're not sure what the parameter is, the best way to figure it out is by looking at the variable that we're working with. So I'm going to go to the data in StatKey so we can look at it. So the data tell us to go to the randomization hypothesis test for single proportion and to choose the NFL wins in overtime games. And if we look at the data, what we have is we've got a categorical variable. We have 240 games that were won by the team that wins the coin toss out of 428 total games. We have a sample proportion of 0.561. That's our sample statistic this time. And so our hypotheses have to be about a proportion. Now we're looking to see if there's strong evidence that the team who wins the coin toss is more likely to win in overtime. More likely to win in overtime means that they would have to win more than half the time. So P is greater than 0.5. And remember, we're always seeking strong evidence in favor of the alternative hypothesis. So this is going to be our alternative hypothesis. Our null hypothesis is going to be, that P is equal to 0.5. We always have the equal sign in our null hypothesis, remember. Okay, so there are our hypotheses written with correct notation. Our observed sample statistic, that is the proportion that were won by the team that won the coin toss in the original data. The notation for that is P hat. And we saw before that it was 0.561. And once again, if you forget where that came from, it came from the original sample here, this 0.561. So there's our sample statistic. Now we're going to generate our randomization distribution using 5,000 simulated samples under the null hypothesis that P equals 0.5. And then we're going to use the distribution to find the p-value for our original sample statistic of 0.561. So let's go to StatKey and do that. So I'm going to generate my randomization distribution, 1,000, 2,000, 3,000, 4,000, come on, 5,000 samples with p equal 0.5 as my hypothesized value. Now, to find my p-value, I need to remember which tail I'm interested in. Since my alternative hypothesis is greater than, I know I'm going to be looking at a right tail. Right tail. And automatically, StatKey is going to pop in here and give me 0.025 in the right tail and show me what will cut that off. But that's not my p-value. To find my p-value, I have to change this cutoff to my sample statistic, 0.561. Now I've got my p-value. It's the proportion of sample statistics that are as extreme as my observed sample statistic or even more extreme. And in this case, it's given up here, 0.0066 is my p-value. So based on the randomization test, 0.0066 is my p-value. Now, we're going to use the standard deviation of the randomization distribution to estimate the standard error under the assumption that the null hypothesis is true. So I'm going to go back to StatKey and pull the standard deviation off the randomization distribution. right up here. So that standard deviation, 0.024, is the standard error of my sample statistics, assuming that the null hypothesis p equals 0.5 is true. Okay, so my standard error is 0.024. Now I'm going to compute my standardized test statistic using my formula. So I'm going to take my sample statistic. Remember, that comes from the original data, and it's our p hat up here, 0.561. Then I'm going to subtract off my null parameter, also known as my hypothesized value. That comes from my null hypothesis. My null value is 0.5. And I'm going to divide by the standard error, 0.024, to get my standardized test statistic. When I punch this into the calculator, it gives me a standardized test statistic of 2.54. That's my Z test statistic. That tells me that my observed sample statistic is 2.54 standard errors away from the hypothesized value. That's what it's measuring for me. So now to find the p-value, I'm going to need to use STAT111, and I'm going to look for the area beyond my standardized test statistic in a standard normal distribution. And I'm going to use the right tail because, remember, I have the greater than sign in my alternative hypothesis, which makes it a right-tailed test. So we'll go back to STAT111. So now in STAT111 I'm using the theoretical distribution for the normal. I need a standard normal. The mean is 0, the standard deviation is 1, so that is my standard normal Z distribution. I'm doing a right-tailed test, so I click right tail. And then I'm going to change my cutoff to find the area beyond my calculated standardized test statistic, which was 2.54. So I'll change my cutoff to my standardized test statistic. And now the area under the curve out beyond that test statistic, 0.0055, that is my p-value. So there are my two p-values, 0.0066 and 0.0055. They're not exactly equal, but they are very similar. Since we're testing at a 5% level of significance, they do lead me to make the same decision about the null hypothesis. They are both smaller than my level of significance, and so I'm going to reject the null hypothesis in both situations. So the answer here is yes, they're similar. Both reject the null hypothesis. So our conclusions to rejecting the null hypothesis in favor of the alternative that p is greater than 1/2. My p-value is less than my 5% level of significance. It is unlikely that I would see data like this by chance if the null hypothesis were true. And so there is strong evidence that in NFL overtime games, the team that wins the coin toss has an advantage. And that's our conclusion. I hope that me walking through the details of this activity help you as you look through your own. If you find that you still have questions, don't hesitate to let me know. Thanks.